Hey, hello and welcome to Equity Education, the chemistry version, and today we're going to be doing some more organic chemistry with alkenes. Okay, so there's quite a lot of information in this, so I would, if I were you, take some breaks just to digest the information that we are going through, but we will go ahead and get started. So I would like you to open your booklets and we will get going. So alkenes are described as unsaturated hydrocarbons, and they contain at least one double C bond, which is known as a carbon double bond. The general formula to work out an alkene is CnH2n, e.g. if I have 3 C's, times it by 2n, gives me C3H6. The functional group, as we've just said, is a carbon-carbon double bond. Okay, some examples of alkenes and naming. So the suffix, so what it ends in is -ene, and I'd like you to have a go at this, so I've drawn some out for you, so see if you can name these. Okay, so let's have a go. First one's pretty easy. 2 alkenes. Pen doesn't seem to be working. Let's try again. There we go. 2 alkenes, 2 carbons, 1 double bond, so eth. We know the ending is -ene, so it must be ethene. 2 carbons, eth. It's an alkene. It's a double bond, so it ends in -ene. So this is my displayed formula. This is a structural formula. Because there's a CH here and no CH2 here, there must be a double bond. 3 carbons, so propene. This is my skeletal formula. Look for the longest carbon chain. 1, 2, 3, 4, 5, 6. So I know it's hex. I have 2 double bonds, so I have to name what position they're on. So 1, 2, 3, 4, 5. So 1, 5. I have 2 of them, so diene. If you're unsure about naming, go back and look at the basic organic chemistry video. Okay, I'm not going to spend too much time on naming here. Again, this is a skeletal formula. It's a cycloalkene, so 1, 2, 3, 4, 5, 6. So this must be cyclohexene. And this one is another displayed formula. So my longest carbon chain is 1, 2, 3, 4. So I know it's bute. This has priority compared to my branch chain, so it must be butene or butanene. And 1, 2, 3. So this must be 3-methyl butene. Okay, alright, so moving on. So testing for a C double bond C. So how do we test for a carbon-carbon double bond? Well, we add bromine water. So Br2 aqueous to an alkene. Might be a gaseous alkene, or it may be an alkene dissolved in water. We don't know, it doesn't matter. We still get the same positive result. So bromine water will go from an orange/brown to colourless. That was right in brackets if an alkene is present. And why does this happen? Well, let's do it with a simple chemical equation or a simple reaction. So here I have my ethene. We'll come on to this mechanism in a bit, but really what we're doing, as you're probably aware, we're going to break this double bond and we're going to add the 2 bromine atoms to my molecule of ethene. So here I have, so this is colourless So this is colourless. The bromine or water is orange-brown. And what I actually produce is 1,2-dibromoethane, which is also colourless, so that's why we see this colour change. So we start with our orange-brown and we end up with colourless. Okay, so that's our test for a C-1C in an alkene. Right, moving on. So, bonding in alkenes. So, bonding in alkenes, they have a single covalent bond contains a sigma bond. So this means sigma. Double bonds, such as carbon-carbon double bond, contain one sigma bond and one pi bond. Pi bonds formed by the overlap of p orbitals, and I'm going to have a go at drawing these for you. So here, these single covalent bonds are represented, or my sigma bonds. These happen, or these occur by atomic orbital overlap, using the s orbitals, and now I'm going to form my p orbital, my pi bond by p orbital overlaps. So you may know that the shape of my p orbital is a bit like a dumbbell. Yeah, so the electrons can be found in any area over here. So I'm going to have a overlap here, and particularly important, which I haven't written up there, is there's a sideways overlap of p orbitals. So I'm just going to write that in here. This should say sideways by the overlap of, no, excuse me, that doesn't make any sense, does it? So by the ovs, try again. So we'll include the word sideways overlap of p orbitals. Okay, so here we have the p orbitals starting to overlap, and when they overlap we form a pi bond. So my pi bonds will look like this, and this basically means that I have formed a pi bond above and below the carbon plane. So this is my pi bond I formed. These are my sigma bonds. Okay, so pi bond, sigma bonds. Okay, so shapes. So alkenes have a bond angle of 120 degrees as the electrons repel as far apart as possible. I'm not going to go into any more detail apart from that. So alkenes are unsaturated molecules. This means that they are generally reactive. And this is because as electrophiles can attack the electron-rich area of the double bond. We'll come on to that in a bit more detail a bit later. Okay, so moving on. Another definition. So stereoisomerism means the same structural, haven't left enough space, formula, but different arrangement in space. We've got two types you need to know. Well, cis strands and EZ, when really EZ is just a special type of cis strands. So cis strands. So this type of isomerism occurs because there is no rotation about C double bond C. So what I mean is, if this is my C double bond C and my C double bonds here, I can't turn it. Yeah, it doesn't turn, so it has to stay fixed like this. You can move them up and down and back and front, but they don't turn. So the carbon atoms in the carbon-carbon double bond are attached to the different groups or different groups. E.g., let's do an example. So say I have, let's do a different colour, methyl group here and a methyl group here, and a H and a H, and we'll do H here, and my methyl groups up here. Now, because there's no rotation about the C double bond C, these two molecules are different, hence why we call it cis and trans. Now, if I can draw a line between my groups going through the double bond, we call this trans. So trans is through the double bond. So this would be an example of trans. However, if it does not go through the double bond, so it's on the same side of the double bond, cis is on the same side. And that really makes sense, because if we have trans, it means through, so for example transatlantic. And if you're trying to work out your cis will be an upside down C, or a smiley face, or a sad face. Okay, so I'd like you to just have a go at naming these. I'll give you a couple of minutes. Okay, so I've drawn this in a different way compared to how you usually see it. And the reason why is because it's easier to see the cis-trans. However, if I'm going to name it, my longest carbon chain will be 1, 2, 3, 4. So I know it's bute. The carbon double bond is on the second carbon, butene. And as we said before, the same group is on different sides of the double bond. So I would call this trans butene. This 1, 2, 3, 4. So it's still butene. However, we would call it cis because the same groups are on the same side of the double bond. Okay, moving on. So EZ. So EZ. Oh, actually, just before we do this, you may see these drawn as skeletal formula, and if I was going to draw the trans version, it would look like this. So this would be my trans, and this would be the cis version. So these are my skeletal formulas. Okay, next, so EZ. So EZ. This type of isomer occurs because there is, again, no rotation about the carbon-carbon double bond. And the carbon atoms in the carbon-carbon double bond are attached to two different groups. Okay, e.g., so this is going to be very similar to my cis-trans, so I'm going to do it quite quickly. Then we'll get on to slightly harder versions of this. So if I do it right, this would be Cl. Okay, so again, we do the same notation or the same working out as we do with Z and E. This would be cis here. Yep, and cis corresponds to Z because it stands for Zusammen, which is German for the same, on the same side. So this would be a Z, which means this would be E. E. Yes. So I'd like you to have a go at naming these then. Okay. Okay. Let's have a go at naming them, which I'm sure you can do. So again, look for my longest carbon chain. 1, 2, 3, 4. So this would be butene, but I also have 2 chlorines, so it's on the second and the third carbon. So this would be 2, 3 dichlorobutene. This would be E3 dichlorobutene. And you may notice that these names haven't changed. This is why they are stereoisomers. They have the same structural formula but different arrangement in space. And we can't tell from the name, just from this part of the name, which isomer it is, hence why we have Z and E, or cis and trans. Okay, now I rushed through that a bit quickly because I want to go on to the Carn-Ingold Prelog naming system. So this can be used in EZ isomerism when all of the groups attached to the carbon atoms in the double bond are different. It works by assigning priority to the groups. The atom attached directly to each carbon atom in the carbon-carbon double bond with the highest, atomic number is given the top priority, the other is given the lowest priority. Okay, so I'll explain by doing an example. Yep, so if we don't have to name this, but let's have FBr. CH3Cl. This would be FCH3Cl, and this would be Br. Okay, so I'm just going to read through this and we're going to apply it to this. The atom attached directly to each carbon in the carbon-carbon double bond with the highest atomic number is given top priority. So we're only looking on one side of the double bond. So I'm looking at the left-hand side to start with here. So which one has the highest atomic number, F or Br? Well, Br does, so this would be high, this would be low. On my other side, I'd be looking at the atom directly attached, so carbon, which has an atomic number of 12, so it's going to be low compared to my Cl, which is high. And then I can match these up. So this would be an upside down C, or a non-smiley face, which would be my Z isomer. And I can do the same thing on this side. So F would be low, this would also be low, this would be high, this would be high, and therefore it would be going through the double bond, which would be the E isomer. So the thing to take away from this is you assign priority on each of the carbons in the double bond. So either low or high, and to do with their atomic number, whichever has the highest atomic number. Okay, so things start to get slightly more complicated if we have longer substituent groups attached around the double bond. So if the groups are similar, work along the group until there is a difference and assign the highest atomic number the top priority. E.g., so if I had H3C on this side and H on this side and CH2CH2Cl, CH2CH2OH, I'll look at this side. Well, carbon is 12, hydrogen is 1, so that's an easy side. So this must be high, this must be low. Here, CH2, 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 CH2. So we have to keep going along this group until we reach an atom that has a different atomic number, or I have a different atom. So here I have Cl and oxygen, so Cl has the highest atomic number, so this would be high priority, this would be low, so high to higher, so it would be a Z isomer. Hope that makes sense. Again, this is quite a lot of information, so you may want to watch this back more than just the once. Okay, so reactions of alkenes. So alkenes undergo lots of reactions, but the main ones they undergo are addition reactions. So in these reactions, the pi bond is broken because it is weaker than the sigma bond. This is usually referred to as the double bond breaking. Right, some more definitions. So electrophiles are electron pair acceptors. So they can be an atom or they can be a group of atoms, but they like electrons. So they accept pairs of electrons. Right, so I'm going to go through this quickly. Okay, so these are all the different types of addition reactions you may need to know. Okay, so you need to learn this page off by heart. So, addition of hydrogen, e.g., if we have ethene, I add hydrogen. This forms, I form ethane by breaking the double bond and adding the hydrogen. The reagents are H2, unsurprisingly. Conditions, I need a nickel catalyst and a temp of about 150 degrees. Okay, addition of bromine, C2H4 plus Br2 would give me C2H4Br by breaking the double bond. I'd use aqueous bromine. This happens at room temperature. And unsurprisingly, you've seen this before, this is how I test for an alkene. Okay, addition of hydrogen halides. I'm going to keep using ethene as my example. Here I'll just use HX, would give me C2H5X, where X is I, Br, or Cl. Okay, so I've made something here. I'm just going to tell you what it is. We would call this a halo alkane because I've added a halogen onto a carbon and hydrogen here, a carbon and hydrogen chain which only has single bonds. So this is forming an alkane. So my reagents would be HX. Obviously I'm not writing down ethene, we need an alkene as well. Conditions, this happens at room temperature. Okay, and the addition of steam, so C2H4 plus H2O forms C2H5OH. You may have noticed this is an alcohol, specifically ethanol. The reagents that I need is H2O gas, so I need it as a steam. And my conditions, so I need a catalyst. So a catalyst is either phosphoric acid or usually concentrated H2SO4. Actually, they're both usually concentrated. But my concentrated H2SO4 would need to be at a temperature of about 300 degrees Celsius. Okay, now I've been through that really quickly. Yeah, I've given you the overall equations and you'd have to apply all of these general equations to work out what the addition of these things are. I will be providing more videos which deal with questions on these topics. Okay, right, so moving on. Oh, one last point. You might notice that most of the conditions are room temperature, and that's because we have this double bond, and alkenes are generally reactive, so we don't have to put that much energy in for these addition reactions. So, addition reactions of hydration and the hydrogen halides. Now, I forgot to mention that we said the addition of steam was adding H2O. This may also be called hydration. And we can also add these. Addition of hydrogen halides may be called halogenation. Unsurprisingly, I think you can probably work this out. This would be bromination. And adding hydrogen would be called hydrogenation. Okay, sorry, I forgot to put them on. Okay, so moving on. So addition reactions of hydration and the hydrogen halides. So these can produce two products if the alkene is unsymmetrical. Okay, so what do I mean by this? Say I've got propene. Actually, can you draw the displayed formula of propene? Okay, so hopefully you didn't draw a protein, you drew propene. It should look like this. Yep, so we have our double bond on the first carbon. So this double bond is going to break, which means that I'm going to add an oxygen and hydrogen to form I'm going to form an alcohol, as shown by here. Yeah, but the position of this alcohol group depends on where I add it here. So I may be able to form add my hydroxy or my alcohol group, means the same thing, on the first carbon here, or I may add it on to the second carbon. So because of the shape of my propene is unsymmetrical, I have actually made two different products, propanol and propan 2-ol. Okay, I would like you to have a go at doing this on your own for butene. So adding HBr to butene and see if you can work out what the two products will be. Okay, I'm sure you've managed to do this. So butene. So this is my butene. I'm adding HBr, so I could add the bromine here, or I could add the bromine atom here. So this would be 2-bromobutane. And remember, I formed a haloalkane because I've added a halogen atom. And bromobutane, or 1-bromobutane. Now, we can form, or we actually form, different varying amounts of these two products. So one will be a major product and one will be a minor product. We'll come on to that in a little bit, but first I want to move on to the mechanism of addition. Okay, so you need to be able to draw this off by heart. So this is a mechanism reaction. So we call this type of mechanism an electrophilic addition mechanism, and it's shown below. Okay, it's not that difficult, but students can't be bothered to learn it and they get it wrong. So I'll start with my ethene, and I'm going to have some bromine. Okay, So my bromine molecule approaches this way round, and that's important. So it's approaching this double bond here. Now as it approaches this electron-rich area, the electrons in my covalent bond here are repelled because they're negatively charged, which means that this becomes, the bromine molecule becomes polarized. So the electrons move further down here, so this becomes delta negative and this becomes delta positive. Now because we have this positive charge here and we have this dense rich electron area here, this double bond will break via heterolytic fission. This bond will then break. So that's our first part of our mechanism, which means our next stage is that I have now broken this double bond. I have formed a covalent bond, technically a dative covalent bond, between this bromine atom. This carbon atom still only has 2 bonds, so it's positively charged. However, I also have a Br on its own. It has a negative charge and a lone pair of electrons because both of these electrons have broken from this covalent bond and gone onto this bromine atom. So I now have a positive charge and a negative charge here, and unsurprisingly we form a dative covalent bond here. So my final product would look like this. So not particularly difficult reaction mechanism, but you need to learn it. You get the marks for drawing the arrows correctly, putting the charges on, making sure you've drawn this intermediate with the carbocation here. If I was going to do the overall equation of this, then I would say that C2H4 plus Br2 has gone to C2H4 Br2. Okay, so all I've done is break the double bond and add my bromine atoms. This is the reaction mechanism to show how I got from this to this. Okay, so we're now going to put it into words. So as the bromine molecule approaches the pi bond or the double bond, the electrons in the covalent the covalent bonds, the electrons in the covalent bonds are repelled here. So it's talking about these electrons here. So the electrons here are repelled because they're approaching this double bond. This induces a dipole, and the bromine molecule has become polarized. And this word polarized, so polarized means that there's a difference in charge. So we have delta negative here, delta positive here, and delta negative here. The electrons from the pi bond are attracted to the positive charge on one of the bromine atoms, and the double bond breaks, which is what we can see happening here. Okay, so stage 2, so we're now on stage 2. Not quite. So a dative covalent bond has formed between the bromine atom and a carbon atom. The covalent bond between the bromine molecule breaks via heterolytic fission. A positive ion and a negative ion form. Right, so we'll just go through this in a bit more detail. Dative covalent bond. So a dative covalent bond is when both electrons come from the same atom to form a covalent bond. Okay, so this must be my dative covalent bond here, because both of my electrons are coming from the double bond to form a covalent bond with this bromine atom. Now at the same time, this covalent bond will break, and it breaks via heterolytic fission because both the electrons from the covalent bond go onto the same atom. And we know it's heterolytic fission because we have a positive ion, so this is my positive ion and this is my negative ion. Again, that's a lot of information. You may want to read through that a second or third or even a fourth time. Okay, so stage 3. So the bromide ion, now it's "-ide" because it's got a negative charge now, is attracted to the carbocation, which just means a positively charged carbon ion, and a dative covalent bond forms. So here's my bromide ion, forms a dative covalent bond with my carbocation here, and we get our product formed. Okay, right, so next bit. I did say it was a long one, this one. So Markovnikov's rule. So Markovnikov. So I'll explain it in a second. So addition of water to butene can produce two products. This is because butene is unsymmetrical. So we've said this before. I don't like the phrase water though, so I'm going to get rid of it because it could be steam. Depends what we're using. We're just going to write H2O. Okay, so I asked you to draw this previously, so we could get this, so we could put the OH here or here. So my OH could go here or it could go here. So I would have butanol or butan2O, as we've previously done, or you have done. Right, however, as I previously mentioned, we can get different products. So the yield of these two products is different. One will be a major product, the other will be a minor product. And it is possible to predict the major and minor product via Markovnikov's rule. Let's see if I can spell it. Markovnikov's rule. So Markovnikov's rules state that the major product will be produced via the most stable carbocation or carbonium ion. You may also see it called a carbonium ion. It means the same thing. So carbocation stability increases the more carbons are attached to the positive carbon. Right. So if you're going to work out this major or minor product, you need to know which one is going to be the most stable carbocation. Okay. Now when we talk about carbocation, I'll just go back up. This would be my carbocation here. Yeah. So it proceeds via the same mechanism. Yeah. Here. But one of the major or minor products will be, well, both the major and minor products will be produced, but one in more amounts. So here we've said that the carbocation stability increases the more carbons are attached to the positive carbon. So that's positive, 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 positive. So that must mean that the stability increases. As we go from left to right, we're adding more carbons that are attached to my positive carbon. And the reason why is because alkyne groups are electron releasing, or you may also see it described of having a positive inductive effect. It means the same thing. I'm going to write effect here. This means the more of them, so we're talking about carbons that are attached to a positive carbon, the more charge can spread out, reducing the positive charge on the carbon, say the positive carbon, making it more stable. Okay, so there'll be a question at the end that you can have a go at doing this, but again, I know this is a lot of information, but I want to get through it, so we'll move on to polymerization of alkenes. Okay, so alkenes undergo addition, polymerization, to produce useful long chain molecules. The double bond breaks, so lots of the monomers can add together. Polymers can be examples of plastics, e.g. so this is my example of my monomer. I'll explain what they are in a second. I can break these double bonds to produce Z, X, Y, Z, and these brackets represent that this will just repeat. So I'd call this a monomer, and this would be a repeating unit. And we can describe these below. So a monomer is a molecule the polymer is made from. The repeating unit, or the repeat unit, is the simplest part of the polymer that is repeated. Not too difficult to understand, really. If you're going to name a polymer, well, it's very easy. You put poly and then put name of the monomer in brackets. Okay, so let's have a go at doing this example. So working out a polymer from a monomer. Okay, so I'm going to say that the monomer is ethene. So this is the molecule that the polymer is made from. The simplest repeating unit of the polymer would be to break my double bond. Whoops, this needs to come out of brackets and show this. So this is my monomer. This is my repeating unit. And usually you need to show at least 2 repeating units to show part of the polymer. Now you can't show all of the polymer because it's a really long molecule, so it would look like this. And this would be N and part of the polymer. And a very quick point is that when you're drawing the repeating units, or the part of the polymer, you must make sure that the bonds come out from the brackets. So bond comes out of the bracket. This is very important. Same thing here. If I was going to name this, well, naming polymers is just poly and the name of the monomer. So this would be called poly. And work out the name of this monomer. That's what the molecule it's come from. It's ethene, so this would be polyethene. Simple. Okay, right, moving on. So working out a monomer from part of a polymer. So I'll let you, you can have a go at doing this, so see if you can work out this. Okay, I'll give you a couple of minutes. Okay, I'm sure you've managed to do this. So the repeating unit is the simplest part of polymer that is repeated. So here we can see there's a benzene attached to a carbon and a hydrogen. So I would say that this, let's take this bit here. This must be my repeating unit. Yeah. So it's repeated here and it's repeated here. So this is the simplest part of the polymer that is repeated, which means if I'm going to draw this, I can take this out, make sure that the bonds come out from the brackets, H, H, H. This would be my repeat unit. Now the monomer, I know it's addition polymers, addition polymerization, so it must have a double bond, therefore this must be my monomer. Okay, right, so a lot of information that we have been through. There are a few questions on the back that I'd like you to have a go at. It doesn't cover everything in this topic, okay, so go away, find some questions, or use my other videos to answer the questions which were provided for alkenes. Okay, so I'll give you 10 minutes to have a go at the questions at the end and then we'll go through them together. But before we do that, I've just realised that we have one last bit to do. So again, this is this is a lot of remembering, so we'll do this quite quickly. So polymers and the environment. So polymers are generally unreactive, which means many are non-renewable. This means it makes them, makes them difficult to dispose of and has led to large landfill sites and also damage to marine life. Recycling. So polymers can be sorted and recycled. This means that less will go into landfill sites. However, sorting polymers can be time consuming and expensive. And that's because we have different types of polymers or different types of plastics, and they're not all recycled in the same way, so they first of all have to be sorted and then attempted to be recycled. Okay, so one way to get rid of polymers is to incinerate them, so incinerating polymers. So incinerate, which just means burning, can produce energy. However, some polymers such as PVC can release toxic gases when burnt. This means any toxic gases must be removed by something called gas scrubbers before any gases are released from burning. And again, I'm not going to go into too much detail about this, it's just something that you need to remember. Chemical feedstock. So feedstock recycling can produce the original monomers from polymers using thermal or catalytic activity. These can then be used again to make new polymers. Pretty self-explanatory, I think. And biodegradable polymers. So polymers made from plant materials. It's usually a plant starch. It could be other things, but we'll just stick with plant starch. Are often biodegradable, meaning that they can be broken down by microorganisms to produce less harmful compounds, such as, no space, water and carbon dioxide. Some plastic bags are now made from biodegradable polymers. Oops, let's see if I can spell biodegradable. Done a lot of writing this video. My hand needs a rest. I'm sure you need a rest as well. Biodegradable polymers. Photodegradable polymers. So these polymers can be broken down by UV light to produce less harmful products. Right, so now we've finished. Again, that's just a lot of remembering just that page. So I'd like to have to go at these questions and we'll go through them once you have finished. Okay, so we'll quickly go through the answer. So draw the skeletal formula of 2-methylpentene. 2, 3, 4, 5. The alkene is on the second carbon. Draw the displayed formula of hex 1,3-diene. So 1, 2, 3, 4, 5, 6. 1, 2. Oh, I've drawn it wrong. That's a good start, isn't it? I have drawn hex 1,3,5-diene. So this should be H, and this should be 1, 2. No, that helps if I do it in the right place again. So let's get rid of that. Let's get rid of that. So 1, 2, 3. So this is where my double bond should be, which means this would be a H. I'd have 3 H's around here, and I had to remove this H here. So let's try again. It's been a long day. So hex 1,3-diene, 1, 2, 3, 4, 5, 6. First double bond is on the first carbon, 1, 2, 3. The second double bond is on the third carbon. That looks a bit better. Draw the structural formula of butene, CH3, CH, CH, CH3. Draw the reaction mechanism for HCl adding to butene. State and explain which will be your major and minor product. Okay, so I left some things off. I left my delta positive and delta negative because I wanted to explain this. So we said in our example that a bromine molecule would become polarized as it approaches this double bond. However, HCl is already a polar molecule. Yeah. However, but it still forms this, follows this reaction mechanism. So my double bond breaks to form a dative covalent bond with my H. This covalent bond will break to form a negative ion here of my chloride ion. Then I'll form a dative covalent bond with my carbocation. Which one will be the major and minor product? Well, 2-chloropropane will be the major product as the reaction mechanism proceeds via the most stable carbocation. So this is what I've drawn here. So it's surrounded by an alkyl group here and an alkyl group here. If it was on the first carbon, then it would only have one carbon attached to it, so it would be the least stable. And polybutene is a polymer used in the manufacture of lubricants and cosmetics. Show the repeat unit, monomer, and part of the polymer. Okay, so I know that the monomer is butene, and I've drawn it like this, and this is a tip. So draw the double bond in the middle, yeah, because we're going to break this double bond here, and this is where we form our repeat unit. So these two break here, which means I have CH3 and CH3 at the top and H at the bottom. So that's my repeat unit. And then I need to draw at least 2 repeat units for part of my polymer. Okay, right, we are done. Now, that's a lot of information. You need to go away and practice that yourself. Okay, so find some past exam paper questions or some just typical exam questions. All the information you need should be in this video to be able to answer them, but you definitely will need to do some practice. Again, I hope that was useful, and I will see you next time. Okay.